Welcome and hello. This is a video exercise in HEC-HMS. And in this exercise, we're going to be dealing with the Mod-Puls reach routing method and using some model calibration from exported data from HEC-RAS. All right, what I have on the screen here is the website we're going to be following along by downloading files and following the steps. I left a link to this webpage in the description of the video if you want to follow along. All right, so first things first, let's just scroll down a short ways and click on this zip file icon, Bald Eagle Creek class underscore initial dot zip. Click the download link, and then that'll download to your browser's default download location. For me, that's over here on the desktop, so I'm going to open that up. What I've got is two different directories. One is HMS and the other is RAS. So that's good. What I want to do is drag those into my target directory where I'm going to be accessing them for this project. Okay, so those copied over fine, they unzipped, and now I can delete the zip file. All right, inside the HMS, we have project files and directories for an HMS project. And then inside RAS, we have the same thing. Bald Eagle Creek is going to be the project. All right, if I scroll down here on the instructions, we have an introduction, a background, problem description, and now we have an outline of the tasks. So these 6 tasks is going to sort of serve as our outline for this exercise in this video, starting with an export from HEC-RAS. So if you haven't used RAS before, you may need to download it to do this first step. Otherwise, you can just watch and see how that works, but it's mostly focused on HMS, this exercise. So just hang in there for the first bit while we do the RAS export and then head over to HMS. All right, so the first step is to open up RAS and then open up the project and basically export some data that's already set up for us. So I'm going to pull the instructions over off to the side here. The first step is to go File and then Open Project. Now I need to navigate over here to my project directory. Okay, so I've got that right here and then click OK. All right, so that's loaded up just fine. The third bullet point down is click on Edit and then Geometric Data. So we have a view of the cross sections, of course, from plan view. And then after that, edit steady flow data. And what we want to do is confirm that there's all the flow profiles are loaded up. There's 11 different flow profiles from half a year up to, I believe, 500 a year. Yep. Okay, so we just had to check that. I'll go ahead and close that. Next, what we want to do is click on the Run menu and then Steady Flow Analysis. And then we want to make sure that this subcritical radio button is selected, and it is already for me. And then go ahead and click Compute. Now it's running the computation that's already set up. Okay, so that's completed. All 11 simulations have run. So we can go ahead and close that window. Next, we're told to view those results, the water surface profiles. So we're going to go up to View and then Water Surface Profiles. And then for the 500-year event, we want to select the options and then profiles right here. And then we have all the profiles loaded at the moment. See, I'm going to clear all and then just scroll down to the 500-year event, double click, or you can click and then arrow over and then click OK. So here is the water surface profile in this Bald Eagle Creek Reach, which is, I believe, 26 miles long. Now we're ready to export the data to DSS. So to do that, we're going to go File and then Export to HEC-DSS. The first thing we want to do is specify the DSS file name. So we're going to be creating a DSS file in the process of doing this export. So go ahead and click on the File Explorer button, and then go ahead and navigate to where you want it, HMS. I'm going to put it in my HMS project. And I know there's some DSS files out here, but to sort of keep it isolated, I'm going to, where do I put it? Okay, I'll put it in here. I'll put it in my data directory. And then I'm just going to call it something generic, but obvious that this is exported from RAS. So I'll just say HEC-RAS exported data.dss and then open. Okay. Before we're ready to export, we now need to also click on the storage outflow tab here. And then what I need to do is specify the 5 different reaches that we're breaking up this entire reach into. So there's going to be 5 separate sections here, and we're going to use those same sections in HMS. Now, the instructions actually give us a screenshot with the actual data to put in. Okay, so I got the table looking just as it does in the screenshot, 5 separate reaches, and then go ahead and export volume outflow data. All right, so that looks like a successful export, close, and then click OK. All right, so that's it for that task. The next task in the instructions is to import storage discharge functions with the HMS paired data manager. All right, so we can go ahead and close RAS now. Sure, we'll save. And then break out HMS. First, I'm going to open up our project. So just navigate to the project that we downloaded. And then here is my HMS project right here. And then I'll click on Bald Eagle Creek class.hms and select. It's telling me that I need to convert to my current version of HMS. So I'll click Convert Project. And our project is now loaded up. Let's break open the basin map. So we see that here. We have a source on top, and then we have a reach 2, 3, 4, and 5, and then finally a sink on the bottom, as we see here in the basin model, which needs to be sorted. Okay, that looks good. So we have the source on top. Also, we have a meteorologic model, control specification, and time series data. And has discharge data, which is the inflow, which I believe is associated with the source, or it should be. Okay, it's not yet. So make sure to click on the source element and then the inflow tab, and then select inflow right here. This inflow value I'm slightly curious about. So it's stored in our HMS project data, bald eagle class.dss, and then this is the path right here. So let's go ahead and take a look at that. I'm going to open up DSS View, and we will be using DSS View at the end of this project as well when we look at some results. Okay, so I'm going to go ahead and navigate to that project, HMS, data, and then this is the class right here. Here's the exported data set, so that might be worth looking at too, but not right now. All right, bald eagle class.dss. And then the path is unsteady flow, 1 hour. So this looks like the stationing number. This is a fairly unique part of the path, like a substring that I could search by, because we have this search bar right here. This could work. Okay, cool. So here's the flow. Perfect. Let's go ahead and take a look at what that inflow hydrograph looks like. All right, so it looks like we're in February 1999, and the peak inflow appears to be around 60,000 CFS. Starts on the 18th, and then looks like the base flow is right at 1,000 CFS. All right, so anyway, so that's what we're going to be using for our source inflow, and then that flood hydrograph is going to be routed through our 5 reaches here. Next, the instructions tell us to add 5 paired data sets, which are going to be used for the storage discharge functions that we exported from RAS for the 5 different reaches. So to do that, we'll go up to the Components menu, Paired Data Manager, and Storage Discharge Functions is the data type we want, so that's good there. Click New, and then what we're going to do is label these reach 1 through 5. So there's reach number 1, and then so that should be populating right there. That's good. Okay, so let's make 4 more here. Next one is going to be reach 2, reach 3, reach 4, reach 5. All right, close that. Now let's open up our reaches and define the data. So reach 1 is the upstream most reach, I believe. Yep. Okay, upstream most reach. So let's click on reach 1. And then what we're going to do is select DSS for our data source. And let's go ahead and look at those 5 reaches that we're going to put in here anyway. So these are the storage discharge curves. I'm going to go to DSS View and just take a look at what those look like. All right, so I'm going to go ahead and open and then navigate to the HEC-RAS exported data.dss. It's right here. Open. Now we have our 5 different paths, which represent the storage discharge relationship for each of those 5 reaches that we defined in RAS and also in HMS. So this first one here is reach 1. I can just tell because it has the highest stationing number for part B. And then let's see, this is actually sorted by string. So reach 2 is here. It'd be nice if it was sorted as a number, but it's not. It's all right. Let's go ahead and take a look at what they are. What we're seeing here is the storage in acre feet along the horizontal axis. And then the dependent variable is on the vertical axis, and that's the flow right here. All right, I'm going to go ahead and close that up. Let's go ahead and make that assignment now. So back in HMS, I'm going to select that HEC-RAS output data and then select. Okay, remember this is reach 1 now. So when I click this button, I need to specify reach 1, which is the largest part B number here, which is the stationing set path name. That's the stationing at the downstream end of the reach. All right, same thing for reach 2, DSS, and then we need to select that DSS file, our HEC-RAS output. And now this is going to be the second largest station number, which is the 75,000 set path name. All right, reach 3, same thing, DSS. There we go. And the button set path name. Okay. And then reach 4. It's going to be right here, set path name. And then finally reach 5, DSS, specify the HEC-RAS output. And then this is the downstream. So this is for reach 5 and set path name. All right. The next task is to finish the data for each of the routing reaches. So what we need to do here is select on each of the 5 routing reaches up in the basin model, and then modify the parameter data in the component editor here. So what we want to do is make sure that the reach is using the routing method modified poles. That's good. And then once that's true, we can select the routing tab. What we want to do for our initial type is say discharge equals inflow, which it is right here. Then we want to set the storage discharge function to that paired data set that we just uploaded right here. So that would be for reach 1. And then for the number of subreaches, the instructions actually tell us what we should use and why. So basically, it's going to be this K value, the travel time divided by delta T, which is the simulation time step, which is 1 hour. So if reach 1 has a travel time of 1.95 hours, we're supposed to use 2. I guess that was a question. So the answer is 2. For reach 2, 1.77 hours divided by 1 hour is rounded to 2 as the nearest integer. We're going to use 2 for reach 3. For reach 4, we're going to use 3. And then for reach 5, we're going to use 7. So that's what it tells us to do. And then after that, we run the simulation. So let's go ahead and knock those out, the number of reaches. So subreaches 1, that looks good. Save. I'll move on to reach 2 now. So I'm going to just confirm modified poles. Okay, routing tab. That's good. Reach 2. And then this is 2 subreaches. Oops, there we go. Okay, reach 3 here. Modified poles. Routing tab. Discharge equals inflow. Reach 3 is the storage discharge function. That looks good. This is also going to be 2 subreaches. Save. And then reach 4. I believe this is modified poles. Okay, they're all that way. Discharge equals inflow. Storage discharge function is going to be reach 4. We're going to use 3 subreaches according to the instructions. And then the last one is reach 5. It's modified poles. Yep. Inflow equals discharge. Reach 5 storage discharge function. And then this is going to be a 7. That looks good. Go ahead and hit save. Now the next task in the instructions we saw was to create a simulation run and then run it and then view the results. So to do that, we'll go up to the compute menu and then we can create a simulation run. Let me see if there's any simulation runs already. Oh, we already have a simulation run. That's right. The instructions tell us this one was made for us already. So that's all ready to go. We can check out the data there, but I trust it's working. So what we need to do is select that uncalibrated simulation right here, which corresponds to the uncalibrated basin model that we've been editing. So we'll click save and then let's run it. And that looks successful. Next, the instructions tell us to view the output and analyze the results. Specifically with reach 5 is what it's showing us. So what it's doing is it's clicking on reach 5. So select that if you don't have it already selected. And then go ahead and click on the graph for that reach. What we see is the inflow and the outflow for that reach. So we notice that there's significant lag and attenuation. If we zoom in, we can get a closer look on what those values would look like. The peak flow, for instance, entering reach 5 is about 58,660, and then exiting reach 5 is down to 57,360 something. We can also click on the global summary table, which I believe is this one right here. Yep, but I need to take off the filter. Okay, there we go. And what we see here is the 5 different reaches, and then it shows the peak discharge. So of course, the peak discharge is 60,000 at our inflow. And then leaving reach 1, then it's down to 59,483. So within reach 1, there was a attenuation of about 516 CFS. And then the attenuation through reach 2 would be the difference between this peak discharge at the bottom of reach 2 versus minus the peak discharge at the beginning of reach 2, which is the discharge of reach 1, and so on. I'm only bringing that up because the instructions are asking some of these questions along the way, which is fine. It says, what is the attenuation in reach 1? 516 CFS. So where it's getting that is the difference between what I just said, 60,000 minus 59,483 or 484. And then it continues asking the same question, I guess, for reach 2, reach 3, reach 4, and reach 5. Now, reach 5 is definitely the largest in terms of attenuation. So we're going to be focusing on reach 5 for the remainder of this exercise. It also asks what's the lag time through the different reaches, and it's 2 hours, 2 hours, 1 hour, 2 hours, and then 6 hours for reaches 1 through 5, respectively. And we can get that data from right here as well. See, there's a 2 hour lag during reach 1, another 2 hour during reach 2, 1 hour, 2 hour, and then 6 hour. Now, of course, we're using a 1 hour time step, so these numbers are not particularly precise. Next, the instructions tell us to compare the results with an unsteady flow HEC-RAS model. The best way I could do this when preparing for this exercise was to just, first of all, go ahead and create a new DSS file. I'm going to put this in my data directory, and I'm just going to call it results.dss, and then click create. Okay, so it's been created. I have a brand new results.dss file up here for me to very quickly and easily organize and compare the paths that I want. And the paths that I want to compare are the target, like actual hydrograph, with the calibrated and initially first uncalibrated results generated from HMS. Okay, so the uncalibrated data that we just generated from HMS, I'm going to bring that up here. So I'm going to open up the project in HMS. Here's my project directory, and inside here I have this uncalibrated.dss. This is the name of the simulation, so the results from the simulation named uncalibrated are going to be stored in this DSS file. So I'll go ahead and click that, open. I'm looking for reach 5 flow, which is this one right here. And keep in mind, this is uncalibrated. It's our first run. So I'm going to go ahead and edit, copy to, and then I'm going to navigate to that results.dss file, which I already have open in my DSS view. So I click open. That open really means copy. So here we have a confirmation, one record copy. I'll click OK. Then I'm going to click on results.dss and then go view, refresh catalog, and boom, here's a copy of that hydrograph. So we'll have that ready and ready for us to compare. Now we need to get the hydrograph to compare to, which should be like the ideal target hydrograph for this particular reach. And that's going to be stored in baldeagleclass.dss. So let me open that up, and it's not in the data directory. Oh, wait, no, it is. It's right there. Okay, I stand corrected. I thought it was going to be in the main project directory because we have some DSS files out here. We also have some DSS files in the data directory. So just be aware of that. So I'll go ahead and select that file. Now I'm looking for reach 5. So I think one of the easiest ways to find reach 5 is to just search for the part B string, which is the stationing. Okay, there we go. So yeah, it looks like it's right here, 659.9 and then flow. Yeah, I think that's it. So let me go ahead and just peek at the data. Yeah, I'm pretty sure that's the one. All right, let's go ahead and go edit. I'm going to copy this to my results.dss just to kind of keep it organized so don't have to mess with this source data. I'll go back to that results.dss file, view, refresh, and now we have our two different hydrographs to compare to. Let's look at what they look like side by side. The instructions seem to focus on peak flow as the measure that we want to calibrate to and match the closest. What we're seeing here in green is the uncalibrated flow. This is the output from HMS, where we're using 7 sub-reaches in that reach 5. And then in red here, this is the unsteady flow. This is the actual target flow we're aiming to achieve. The instructions tell us to adjust the number of sub-reaches where necessary and rerun the HMS model. And it then goes on to tell us to make a copy of basin 1, call it calibrated, and then modify the number of sub-reaches in each of the reaches so that we get a better match when comparing those hydrographs. So let's go ahead and do that. I'm going to leave this right where it is, minimize DSS view, and then I'm going to select this uncalibrated routing for the basin model, and then just right click, create a copy. And then I'm going to call this calibrated like it told me to, and then copy. So I'm going to just collapse that, expand my new calibrated basin. And then for reach 5 here, I'm going to go down to the routing tab and change this 7 to something smaller than 7 because we need more attenuation. And I'm just kind of going to guess 3 and then save. Now I didn't check reaches 1, 2, 3, or 4, and that's fine. This I think we're going to learn it enough just doing this. And then I'm going to create a new simulation run. So compute simulation run manager, new. I'm going to call this calibrated because it's going to be using the calibrated basin model. And then next, so I'll be using the calibrated basin model. There it is. And the one and only met model, the one and only controlled specification, and that should be good right there. Okay, so next we're going to run the calibrated model. So I'll select that and then run. Okay, so that looked like it ran. I'm going to view the results via DSS view. And to do so, I'm going to open up the DSS file associated with that simulation run. So I'll go open. And then here is our calibrated.dss file. That's good. I'll open that. And now I need to search down to reach 5 flow. I could open it up here. Doesn't look like there's much improvement, but let me compare it first. And so go edit, copy to. I'm going to navigate to that results.dss file. Okay, the copy's been made. Let's go ahead and refresh this, refresh catalog. Okay, so now we have our target. This is our run with 7 subreaches, and this is the run we just did, calibrated with just 3 subreaches. So let's go ahead and view those all together. Plot. We've made a minor improvement. Here is the target down here. In red, this is 7 subreaches, and green is 3 subreaches. So we need to reduce the number of subreaches again, maybe 2 or even 1, and then let's run it one last time. Before I do that, what I want to do is rename this path, maybe just part F, so it's easier to identify. Instead of calibrated, I'm just going to say n equals 3 for the number of subreaches. Okay, it's been renamed. And then also for this one, I'm just going to go rename part F. I'm just going to append n equals 7 because that's actually a little bit more meaningful for me. And okay. All right, let's go back to HMS now. And we're going to make one more copy of the basin model. So calibrated, create a copy. I'm just going to call it calibrated 2 for lack of a better name. So I'll collapse calibrated, open up calibrated 2, select reach 5, come down to the components editor, confirm that we're using modified poles, click on the routing tab, and then switch this number of subreaches to just 1. We'll see what happens with that. So save. Now let's create a new simulation run. So new, and then I'll call this calibrated 2. Next, it's using the calibrated 2 basin model with the new 1 subreach and reach 5. Next, next, next. Okay, good. Now let's select calibrated 2 and run it. All right, so that's done. Let's go back to DSS view. Let's open up the calibrated 2 data, which is right here, and open. All right, and reach 5 is right here. Let's just edit, copy that to our results.dss file. Boom, that's been copied. And then let's refresh. So this is going to be, let's just rename it first. I'm going to append n equals 1 here, and then OK. All right, let's look at all the paths together. This looks like much improvement, so that's satisfying. The peak discharge in the blue line here is the target. This is what we're going for. And then the yellow line here was n equals 7. This is our first run, the quote uncalibrated run. The second trial was n equals 3 with 3 subreaches. And the run we just did right now was n equals 1, which actually looks like it's a little bit below the target. So n equals 2 may have looked pretty good as well. If you want to do that yourselves, by all means, go ahead. But I think we've done enough calibration in this exercise to get a feel for what it means to use reach routing, specifically the modified Puls reach routing method, and then modify some parameters here to get a pretty good match when calibrating our data with a known hydrograph.